Hi guys, my name is Ashley Chapman and today I'm going to be solving an application optimization problem that uses derivatives for optimization. Our goal of this problem is to find the maximum possible volume of a box made from a piece of cardboard. Okay, so our specific problem says a box with an open top is to be constructed from a 12 by 10 foot rectangular piece of cardboard by cutting out squares or rectangles from each of the four corners and bending up the sides. Find the largest volume that such box can have. So first thing we're going to want to do is draw out our cardboard box. So we have the squares that we're going to be cutting out, and those are going to be represented by X, as well as the length, which is 12 feet, and the width, which is 10 feet. And our goal is to determine the size of the cuts here, represented by X, that will give us the largest possible volume. So after cutting out squares of side length X, the height of the box becomes X. And the length, 12 feet, and the width, 10 feet, are reduced by twice X since we removed one square from each side. This gives us a length of 12 minus 2x and a width of 10 minus 2x. Next, we are going to identify our volume function, which for a cube is length times width times height, or height times length times width in this case. And this function represents all possible volumes of the box depending on how large the cuts from the squares in the corner are. Our next step is going to be to simplify this volume function by multiplying all three x's. Our simplified volume function after multiplying everything out is 4x cubed minus 44x squared plus 120x. Simplifying this volume function makes it easier to differentiate when we expand the expression. So now we're going to take the derivative of our simplified volume function, and that derivative is going to be 12x squared minus 88x plus 120. And so this derivative volume function right here is going to tell us the rate of change of the volume, and setting it equal to 0 will help us find where the maximum volume occurs. So to find where the maximum volume occurs, we're going to find the critical points, and to find the critical points, we're going to set our derivative volume function to 0. And because this function does not factor out, we are going to use the quadratic formula. And so here is our quadratic formula right here. X equals negative b plus or minus square root of b squared minus 4ac all divided by 2a. So when we plug that in to the quadratic formula, we get x equals 2/3 feet and 5 feet. Now, if we refer back to our box here, we can see that there are some physical constraints to our two answers here. If we think about this in a literal sense rather than a mathematic sense, it wouldn't make sense for this square cut out to be 5 feet because that would be the width of the rectangle. So our only possible answer is going to be 2/3 feet for x. Now that we have our answer for x, we're going to plug it into our original volume function. And plugging this in, we get 18.96 cubic feet. So from this solution, we can concur that the largest possible volume occurs when we cut out squares that are 2/3 feet by 2/3 feet. And this problem demonstrates how derivatives can be used to optimize real-world designs and problems and applications. This problem also shows why it's important to consider physical constraints when solving application problems. Thank you for watching.